Okay guys, so let's begin our discussion over the JEE main pattern exercises for permutations and combinations. First question says that if n factorial, 3 into n factorial and n plus 1 factorial are in GP, then what is the status of n factorial, 5 into n factorial and n plus 1 factorial? So it's given to us that these three terms are in GP, that means the square of the middle term is equal to the product of the extremes. So what you get basically is 3 into n factorial whole square is equal to n factorial into n plus 1 factorial. Why? Because these three are in geometric progression. So this becomes 3 square 9 n factorial square. This becomes n factorial into, this becomes n plus 1 into n factorial. So obviously n factorial whole square gets cancelled out from both sides. You are left with 9 is equal to n plus 1, or n is 9 minus 1, that is 8. Question is, what is the status of n factorial, which eventually becomes now 8 factorial, 5 into n factorial, which becomes 5 into 8 factorial, and n plus 1 factorial, which is 8 plus 1 factorial, that is 9 factorial. Just by looking at these terms itself, it's very, very easy to analyze that twice of 5 into 8 factorial is equal to 8 factorial plus 9 factorial, which eventually means that these three terms, given terms, are actually in arithmetic progression. So the moment value of n is out, it's very, very easy to understand that how twice of the middle term will be equal to the sum of the two extremes, and hence the 3 will be in arithmetic progression. Clear? Next question says that if n minus 1 CR is equal to k square minus 3 times n CR plus 1, then k belongs to which interval? Which interval does it belong to? So let's see. This is k square minus 3 will be equal to n minus 1 CR upon NC R plus 1. Clear? Just open this up. This is n minus 1 factorial upon R factorial into n minus 1 minus R factorial. Then this is n factorial R plus 1 factorial into n minus R minus 1 factorial. Right? Because it is n minus of R plus 1, which is n minus R minus 1. So over here what do you basically get is, this is n minus 1 factorial whole upon, and here you have R plus 1 into R factorial. Right? This becomes n minus R minus 1. This is n minus R minus 1 factorial whole upon, this is R factorial, n minus R minus 1 factorial, and then this is n factorial. So you can see R factorial gets cancelled out. This becomes n into n minus 1 factorial. So n minus 1 gets cancelled out. This gets cancelled out. You are just left with R plus 1 by n. So you get k square minus 3 is equals to R plus 1 by n. Now what is this R? What is this R? R is actually ranging from 0 to n minus 1, greater than equal to 0, less than equal to n minus 1. Right? It's greater than equal to 0, less than equal to n minus 1. So what about R plus 1? R plus 1 will be ranging from 1 to n, and therefore R plus 1 by n will be ranging from 1 by n to 1. Clear? The moment you get this, you have got the very range for k square minus 3 itself, because that is what is equal to R plus 1 by n. So you get that k square minus 3 is less than equal to 1 and greater than equal to 1 by n. So you get 1 by n plus 3 is less than equal to k square is less than equal to 1 plus 3, that is 4. And this term is strictly greater than 3. N is positive. So k square is strictly greater than 3 and less than equal to 4 means that k is lying between root 3 and 2. So k basically belongs to open root 3 closed 2 interval. Open root 3 closed 2 interval is the very interval in which k belongs. Next question says that a gentleman has 6 friends to invite. In how many ways can he send invitation cards to them if he has 3 servants to carry the cards? Now see, it's pretty simple just if you understand the logic. So there are 6 friends of this gentleman. 6 friends of this gentleman, and there are 3 servants who are carrying the cards. And invitation cards have to be gone to all the 6 friends of this particular gentleman. Now what can happen is, out of these 3 servants, any servant can go to give the invitation card to the first friend, right? That means the task of giving invitation card to the first friend can be accomplished in 3 ways. The task of giving an invitation card to the second friend can also be accomplished in 3 ways. Out of the 3 servants, anybody can go and give the card. So the second task can also be accomplished in 3 ways. Similarly, third task can also be accomplished in 3 ways. Fourth can be accomplished in 3 ways. Fifth can be accomplished in 3, and sixth can also be accomplished in 3 ways. My task is to actually give invitation cards to all the 6 friends, right? That means all the tasks need to be performed simultaneously, or I can say once you are done performing the first, go and perform the second. Done performing the second, go perform the third. Done performing the third, go perform the fourth, and so on. That means when one job is done, then go and perform the next job. That means all the jobs need to be done. That means this and this and this and. That means multiplication rule is going to come into picture, and you are going to say that if individually each task can be done in 3 ways, all the 6 tasks together can be done in 3 to the power 6 ways. Clear? So your answer is 3 to the power 6. Next question says what? Let's see. How many 5-letter words with or without meaning can be formed out of the letters of the word equations if repetition of the letters is not allowed? Now see, equations is made up with how many letters? 9 letters. I want to make 5-letter words. 5 letters can be selected out of 9 letters, out of which all are distinct, in 9C5 ways. So the first job is to select any 5 letters from the given 9 letters. That is the first job. So I have selected 5 letters out of the given 9 letters in 9C5 ways, right? Now the selected 5 letters can be arranged in how many ways? In 5 places. All are distinct, right? That means no repetition is being basically taken into consideration. So the moment I have selected 5 letters from the letters of the word equations, there are 9 letters in that. Now how can I arrange these 5 letters in 5 places? I can do that in 5 factorial ways. So each of these selections is giving me 5 factorial arrangements. So these many selections are giving me these many into 5 factorial arrangements of the letters of the word equations, right? Or basically I can say this is actually the total number of ways in which any 5 letters out of the 9 letters given over here can be arranged. Fine. So your answer is 9C5 into 5 factorial, which comes out to be 15120. So 2 jobs were there. First you select 5 letters, then you arrange those 5. Both the jobs need to be performed, so multiplication rule came into action. Then you have, let A and B be 2 sets consisting of m and n elements respectively. The number of one-to-one functions from A to B are how many? So understand, if that's A, that's B. So you basically have A1, A2 up till AM, and B1, B2, BM, BM plus 1 up till Bn. Why? Because m is less than n. Now you want 1-1 functions. So for 1-1 basically you need that each element of set A should be mapped to a distinct element of set B. No 2 elements should be mapped to the same element. That means if there are m elements over here, minimum to minimum there should be m elements over here. Out of these n elements, m elements can be chosen in how many ways? That would be the first task. Out of these n elements, I will first choose m elements, right? So that can happen in NCM ways. First set of m elements has been chosen out of the given n elements. Now I have m elements with me. These are m elements. I can basically map in how many ways? In how many ways can I develop the mapping? from the members of set A, which are m in number, to the selected m members of set B, that can be done in m factorial ways, right? It's almost like m elements are being arranged in m distinct places. So that can be done in m factorial ways. So each of the selection of m members out of the given n members is going to contribute to give you m factorial 1 functions. So there are these many ways in which you can select m members out of the given n members in set B, each contributing m factorial 1 functions. So total number of 1 functions is this into this, and that is your answer, which is NCM into m factorial. Next we have the number of arrangements that can be made with letters of the word mathematics in which all the vowels come together. So how many vowels are basically there? You have A, you have E, again you have A, again you have I. So there are four vowels and you want all these four vowels to come together, and now you are left with 1, 2, 3, 4, 5, 6 and 7. 7 letters. So you have M, T, H, M, T, C, S. So what you basically do is you have A, E, A, I. You basically consider all these four vowels as one single letter, because wherever they are going to go, they are going together. Yes, that is what I want. I want these four vowels to be always together. So I consider all these four vowels to be one single letter. Now if you consider this to be one single letter, you are left with 1, 2, 3, 4, 5, 6, 7 and 8 letters. These 8 letters can be arranged in 8 factorial upon, why upon? Because there are 2 T's and 2 M's. These many ways. But this is corresponding to one of the arrangements of these four vowels. These four vowels, if arranged in this order of A, E, A, I, are giving rise to 8 factorial upon 2 factorial into 2 factorial arrangements of the letters of the word mathematics in which the four vowels come together. But it's not just this way that these four vowels can be arranged. There are how many ways of arranging these four vowels? They can be arranged like A, E, A, I, E, I, E, A, I, A, E. So many ways. There are actually 4 factorial upon 2 factorial ways of arranging them. Each of those arrangements of these four vowels is going to give me these many arrangements of the letters of the word mathematics in which vowels come together. So when I add all of them, I mean this plus this plus this, how many times? 4 factorial upon 2 factorial times, I get this multiplied by 4 factorial upon 2 factorial is the total number of arrangements of the letters of the word mathematics in which the four vowels come together. So that's my answer, and it is given to you as 8 factorial into 4 factorial upon 2 factorial cube. Okay? Next question says that the total number of proper factors of 7875. So we've done this concept. How do you get this? So total number of proper factors of 7875. You can very easily factorize. You get 3 square, 5 cube, 7 to the power 1. Now how many factors are there? 3 into 5 into 7 is one factor, 3 square into 5 into 7, or 3 square into 5 square. That means I am wishing to choose one or any number of objects out of the 2 objects of one kind, 3 objects of the other kind and 1 different object. In how many ways can I do that? I can do that in 2 plus 1 into 3 plus 1. And then 1 is distinct, so 2 to the power, how many are distinct? Minus 1. That is how you can choose one or more objects from the available P objects of one kind, Q objects of the other kind, and N rest of them distinct objects. So here I have this as P, this as Q and this as N. So that is P plus 1 into Q plus 1 into 2 to the power N minus 1. So you basically get 3 into 4 into 2 minus 1. So you get 24 minus 1, that is 23. But the question is about proper factors. This is total number of factors. That means one of the ways of choosing is choose all of them. In which case 7875 itself is going to be the factor of itself. I don't want that factor, so proper factors will be 23 minus 1, which is 22. Clear? What is the next question? Let's see. The number of ways in which a pack of 52 cards can be divided equally among 4 players in order. So there are 4 players, and in order I have to basically distribute these 52 cards among these 4 individuals. Now the first time I go and distribute cards to, I want to distribute equal number of cards to all the 4. Obviously 52 divided by 4 is 13, so each one is going to get 13 cards each. Fine, the first person, the first guy I go to, and I can distribute him 13 cards out of the available 52 cards in 52 C 13 ways. The moment I have done that task, I now go to distribute 13 cards to the next one. So I am left now with not 52 but 52 minus 13, which is 39 cards. Out of these 39 cards, I will distribute him 13 cards in 39 C 13 ways. Once I am done with this task itself, then I am going to go to the third guy, and now I am not left with 39, I am left with 39 minus 13, that is 26 cards, and out of which I am going to distribute him 13 cards in 26 C 13 ways. And then I am going to go to the fourth guy, I will only be left with 13 cards, so I am going to do that in 13 C 13 ways. Because I want to perform all the 4 tasks, each guy should get 13 cards each, so perform the first task first, and then perform the second, and then perform the third, and then perform the fourth. And therefore multiplication rule comes into picture. You basically get what? 52 factorial upon 13 factorial whole to the power 4. And that is what is your answer, which is 52 factorial upon 13 factorial to the power 4. Clear? Next question we have the number of ways of distributing 5 identical balls in 3 boxes so that no box is empty. Now this is a pretty direct concept. If you remember, what are the number of ways of distributing n objects in R groups such that each group contains at least one object? That means no group is kept vacant or no group is kept blank. That can be done in n minus 1 C R minus 1 ways. Exactly same thing is kept over here. 5 identical balls are here, and you want to distribute 5 identical balls into 3 boxes. So 5 identical objects, 3 groups, that can be done in 5 minus 1 C 3 minus 1 ways. So it is what? 5 minus 1 C 3 minus 1, which is 4 C 2, which is 4 factorial upon 2 factorial into 2 factorial, which is 6. So there are 6 ways to do so, so your answer comes out to be 6. It's a pretty direct concept, no need to get confused in this. Next question we have the number of ways in which 5 letters can be placed in 10 marked envelopes so that no letter is in the right envelope. So there are 10 marked envelopes and there are 5 letters which can be placed in these envelopes. What is the very number of ways in which you can place them such that no letter is in the right envelope? That means you want to not arrange them in the correct fashion, you want to de-arrange them. So number of ways in which these 5 letters are not put in the correct envelopes is equal to the number of de-arrangements of the 5 objects. What are the number of de-arrangements of the 5 objects? It is nothing but 5 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial. And this number comes out to be 44. So 44 is the total number of ways in which you can de-arrange 5 objects. And that is what is being asked in the question, because you don't want to basically arrange these 5 letters correctly. Right, so you want to de-arrange them. So concept of de-arrangements comes into picture, and that is your answer, that is 44. Clear? So all the concepts are thus covered in the questions. Fine, so practice them very nicely. That's it from my side. Thank you.